Hello again, and welcome back for the third installment of Mr. Wojciechowski Teaches Calculus. So the first thing that I have, it would have been the do now in class, but just like use what continuity sounds like to figure out where this function is discontinuous. Maybe pause, give a couple of guesses, then when you unpause, I'm going to tell you that there are 3 places where this function is discontinuous, and then maybe you'll have to find the third one because you might have only had 2. All right, cool. I'm going to show you the 3 places where this function is discontinuous. So just to be clear, this function is continuous everywhere where it is not discontinuous. So the discontinuities occur at x equals -2 and x equals 2. Because we have this kind of like right here where it has to jump to get up here. So it's got that break in this graph. Discontinuity means you have to pick your pencil up in order to draw the function. So discontinuous at x equals -2, and again at 2 we have that you have to pick up your pencil to draw it. And I'm wondering if anybody got the third place where this function is discontinuous. This function is also discontinuous at 5. We have specific continuity definitions at endpoints. Since we've got this open circle, we do not have continuity at 5. So the 3 places where this function is discontinuous are at x equals -2, x equals +2, and x equals 5, because at each of those locations we have to pick up our pencil to draw the function. So skip over that. We would have had a homework quiz if this was actually in-person learning. But here we have some continuity. So most techniques in calculus require that functions be continuous. There's a lot of things that fail to be possible if we have discontinuous functions. So we have to be able to identify where a function is continuous. And I kind of gave you this definition before. A function is continuous if you can draw it in one motion without lifting your pencil. Any point where you have to lift up your pencil, that is going to be called a discontinuity. A function is continuous at a point if the limit is the same as the value of the function. For a more formal definition, and I would probably put this formal definition into my notes, it's on page 79. I'm stealing it right out of the textbook, putting it on my dot cam, so that you guys can see exactly what I'm talking about. Continuity, a function is continuous at an interior point, so that means a non-end point, if its domain, if the limit as x approaches c of f of x is equal to f of c. It is continuous at a left endpoint or continuous at a right endpoint if limit as x approaches a from the right of f of x is equal to f of a. That's where it's continuous at the right endpoint. Or the limit as x approaches b from the left of f of x is equal to f of b. So that's it being continuous at a right endpoint. So again, I would probably insist that you guys write that in your notes because that's some important stuff. If a function is not continuous at a point, we say that f is discontinuous at that point. And C is a point of discontinuity. A lot of times we just call it a discontinuity, not a point of discontinuity. But, I would accept either one. So what I'm trying to get at here is kind of what we did on the first section in this chapter, where we said, there's my black pen, in case you guys were wondering what I was looking for. The first section of this chapter, where we had to set up like 4 different problems, where we had the limit as x approaches some point, and according to our book, they were just using c of f of x equals something. The limit as x approaches, c from the left, approaches c from the right of f of x equals a number. Limit as x approaches c of f of x. Remember in the first section we said if these 2 numbers are the same, then this is the same as these 2. And then we had that third question where we had f of c. Fourth question, not third question. And if all four of these numbers are the same, remember in the first section, we really didn't care about this in order to answer these three questions. But if this is the same as these other three, then the function is continuous. So just to give you an example, I can flip back to, let's say, section 2.1. All right, cool. So I'm looking at number 39 right there. That function, I know that it is discontinuous at the point x equals 3. And why is it discontinuous? Because I run through these four questions. First question, limit as x approaches 3 from the left. Well, that is 3. Limit as x approaches 3 from the right. That is -2. Limit as x approaches 3 of f of x. Well, since a and b were different answers, we have c does not exist. And d was 1. Let's look for something that gives us a continuity. Like number 41 right here. 41, we have the limit as h approaches 0 from the left of f of h is, coming in from the left at 0, that's -1, 2, 3, 4. So a is 4. Coming in from the right, same value. So b is 4. C, since a and b are both 4, c is 4. F of 0, what's colored in? It's at a 4. Basically, the definition of a limit says as long as the function value equals the limit value, the function is continuous. And just looking at it, I can tell that I can draw that without lifting around my pen. I can also see on number 42 that I have to lift up my pen at 0. Number 43, lift up my pen at 4. Now 44 is kind of tricky. Again, this is on page 67 if you're trying to follow along with me. This one is focusing on the x approaches 2. I can see definitely that this function is discontinuous at 0, but at 2, I try to answer these four questions. Limit as x approaches 2 from the left. Well, that is coming in from the left. Again, I don't care what's colored in here. That's 1. Coming in from the right, I have, okay, that's 1 again. So I have the limit exists, and that limit exists at 1. C, the answer is 1. For D, though, when I look for what is g of 2, it's colored in at 3. Since C does not equal D, the answer is this function is discontinuous at 2 as well. Just trying to bring that back to some stuff that we had learned before to show finding out if a function is discontinuous or continuous at a particular point is not too hard informally, but formally you just have to check, does the limit exist and does that limit equal the value of the function at that point? So let's look back over, turn off sphere, and let's go over here. There are several different types of discontinuity. That last example that I showed you, number, I think it was 41 or something like that on page 67, that was called a removable discontinuity. And a removable discontinuity, you guys learned it last year as a hole. So, here are two examples of discontinuities. This guy right here, and this guy right here. It doesn't matter if there's a value of the, if there's a value for the function at the point C, as long as there's that hole right there, it's a removable discontinuity. Both of these are removable discontinuities. And to remove them, all I have to do is bubble in the hole. The removable discontinuity is probably the cream of the crop when it comes to discontinuities. Those are the ones that we want to see. There can be good stuff that happens at removable discontinuities. These other types of discontinuities, these just cause all sorts of calculus to fail, like a jump discontinuity. A jump discontinuity or a finite discontinuity is called a finite discontinuity because the distance between the break, you can count it. It's right here. It looks like the function jumps a little bit. You're going here, and then there's this break. You have to spontaneously jump up there. An infinite discontinuity refers to the distance, again, between the left side of the discontinuity and the right side of the discontinuity. When we look at an infinite discontinuity, you know those as vertical asymptotes. So I'm telling you right now that instead of calling them vertical asymptotes, we're going to call them infinite discontinuities from here on out. And the last one that's really hard to see, I mean, you can grab your calculator. I can show you the discontinuity. It's kind of rough to see, especially like even on a calculator. Let me pull this up here, and I'm going to go to my, let's see here. Sorry, forgive me here. Y equals menu. I'm going to clear that out, and I'm going to plug in sine of 1 over, not alpha, x. That has a discontinuity, and just looking at it personally, I can see that there's a discontinuity at 0. Can anybody figure out how I know that there's a discontinuity at 0? All right, cool. I'll tell you. It's because I have a divide by 0 error right here, right at the 1 divided by x, where x is equal to 0. I'm going to divide by 0. So, looking at that graph, it doesn't really look like there's a discontinuity there, does it? In order to see this discontinuity, you actually have to zoom in a crap ton. So I start zooming in, and I can start to see that there's a little bit more of that oscillation right there. Zoom in again, and I can see that it's bouncing back and forth. If I zoom in enough times here, I can actually see that as this function gets closer and closer to 0, I start to get more and more infinite oscillation for it. So that is called an oscillating discontinuity, which is, in my humble opinion, which I don't know which side of that debate you guys land on, whether it's my honest opinion or my humble opinion, but in whichever type of opinion I have, the oscillating discontinuity is the most difficult to see. Now, I will tell you, in order to get any of these discontinuities, there has to be some sort of either a piecewise function that causes a break in the rules or a divide by 0 error. So there should be some sort of fraction where we have a 0 in the denominator. Or we should have some sort of piecewise function, and if it's a piecewise function, the only place for the discontinuity to occur, as long as the pieces are continuous, would be at the change in the rule there. All right? So let's go back to active board. And I want you guys to work on exploration 1 on page 81. Probably pause this screen, come back to it. I believe I have, yeah, okay. That's just a piece of the graph for exploration 1. So don't worry about that right now. Again, pause your screen, do the exploration, and then come back to it, or come back to me, unpause, and I'm going to go through the exploration. So that's going to be right Chahira. All right. I hope you guys know how to factor a denominator. If you don't, yoicks. So I'm looking at my f of x is equal to x cubed minus 7x minus 6 over x squared minus 9. All right? So factoring the denominator of f, we are going to get x cubed minus 7x minus 6 over difference of squares, x plus 3 times x minus 3. Remember last year in trig precalc, y'all learned that the domain of a function is wherever the denominator is not equal to 0. That pretty much causes every domain error that exists. And what I look at here, where the denominator is equal to 0, so I think A was asking, what is the domain of f? So my domain is all x, so it's all real, where x is not equal to, well, what makes this equal to 0? That would be -3. What makes this equal to 0? +3. X equals plus or minus 3. My domain is all reals where x not equal plus or minus 3. All right, that's the real numbers symbol. x not equal to plus or minus 3. Let's look at what B has. Investigate the graph of f around x equals 3 to see that f has a removable discontinuity at x equals 3. Okay, so will I see that I have to investigate a graph? If I'm investigating a graph, I'm going to pull out my bad boy calculator right here. I've got x cubed minus 7x minus 6 over x squared minus 9. I hit my graph, and it graphs slowly, so I can see that infinite discontinuity right at x equals negative 3. Remember, we said the domain is all reals where x not equal to 3. So that negative 3 is right here as an infinite discontinuity. I keep graphing. Ooh, but oh man, at x equals 3, it looks like this function is continuous. That scares me. Scares me so much. All right. So in order to investigate the behavior around 3, again, it looks continuous at 3. To see that it is indeed discontinuous, the function is discontinuous at 3, I go to trace and I type in 3. And I see there is no value for y at x equals 3. That means there's a discontinuity here. If I keep tracing and go left, go right, the function is defined everywhere around 3, but not at exactly 3. So that is how we can show for number 2 that f has a removable discontinuity at 3. How do I find it? How do I find what the value is to remove the discontinuity? Well, it tells me right here. I can zoom in, use tables. Well, if I'm using my table, in order to find out what the value is that I want to plug in there, I want to plug in something really close to 3. What's really close to 3? 2.999999999. Other thing that's close to 3? 3.000000001. Boom. I can see that the value should be 3.333333. Or if I'm thinking in terms of fractions, 10/3 is what that would be. I'm kind of cheating. It says the answer down here. Really what I'm looking at for B, use graphing calculator. For C, what I'm looking for in order to fill the hole in that function, I'm looking for what's the value really close to 3 for this function. In order to fill the hole, one cheat that you can do is find the limit as x approaches 3 of the function and just force the function to equal that value. So here, I find the limit as x approaches 3 of f of x is equal to 10/3. Cool. That's the value that it should be in order for this function to be continuous. So if I was able to color in on the graph at 3, 10/3, I would fill in that hole that is there that we can't really see. Let me see. Zooming in, I think, actually helps us see this a little bit better, too. If I'm zooming in on 3, zoomed in a little bit, and it's graphing slow. That's fine. We got all the time in the world. And again, here's 3. We can see right about there. X equals 3. I can put right on the, well, actually, let's go here and use the trace. I can see it's straddling that 3.333. I can zoom in even further. By the way, if you've never used zoom before, you have to put the crosshairs where you want it to zoom before you actually hit enter for it to zoom. And if it's not zooming, it's because you didn't hit enter. Oops. And again, there's the tick mark for 3. I believe that's also the tick mark for 3. This would be at about 3 1/3 or 10/3. It looks like I can get pretty dead on to 3 if I match up on the line. It looks like I'm at 3.33, and then carry on, carry on. So again, I wasn't really doing any math there, but the next thing that I have to do is show that x minus 3 is a factor of the numerator of f and remove all common factors. So basically what I'm looking at here is I know from trig precalc, the way that we tried to eliminate holes, I know that I'm going to have since x minus 3 represents the whole, I know x minus 3 has to be a factor up top over x plus 3 times x minus 3. And you should remember that from trig precalc, that once we get that, we can cross those off and we can figure out where the whole is. This is how we can algebraically figure out what the what that should be. Now, there are a bunch of ways to figure out what this value is, but I happen to know that since I'm going to have x cubed over here, this is going to have to be an x squared. Since I have minus 3 over here, I happen to know that this is going to have to be plus 2, just because I know how foiling works. This is going to be some sort of trinomial, and negative 3 times 2 is going to give me that negative 6. Now all I have to figure out is how am I going to get that minus 7x, and also to get a 0x squared out of this. And I just play around with it. I know that the factors that are going to give me an x, I know that this middle term is going to have an x as well. So minus 3 times x, and sorry, minus 3 times whatever x, and x times 2 should add up to give me negative 7x. That can't be right. Okay, I know that works sometimes. Let's see, x minus 3 times x squared, gonna have to have a plus 2 over there. That gives me that minus 6 x 2x and oh, it's positive 2x. Okay, cool. So this is going to have to be plus 3x. You can also do that using long division if you wanted to. And again, just looking at that, I've got x cubed. I've got x times 3x gives me 3x squared. Negative 3x, negative 3 times x squared gives me minus 3x. X times 2 gives me 2x. Minus 3 times 3x gives me negative 9x, which gives me that negative 7x. And minus 3 times 2 gives me that minus 6. And in the denominator, I had that x plus 3 times x minus 3. And we can cross those off. And all of a sudden, we're left with show that x minus 3 is a factor of the numerator. Boom. And remove all common factors. Now compute the limit as x approaches 3 of the reduced form for f. So now what I can do, I can have the limit as x approaches 3 of f of x is going to be equal to the limit of this. So that would be equal to the limit as x approaches 3 of x squared plus 3x plus 2 all over x plus 3. And now I'm going to try my d sub. I've got 3 squared plus 3 times 3 plus 2 all over 3 plus 3. 9 plus 9, 18 plus 2 gives me 20 over 3 plus 3 gives me 6, 26 or 10/3. So now what I have algebraic confirmation that the limit as x approaches 3 of f of x is indeed equal to 10/3. The extended function now, that was number 4. Now the extended function, this is one way that we can eliminate a discontinuity. This is basically how we color in the bubble. We say g of x is equal to the original function wherever it's not a removable discontinuity, and then we plug in just the limit where x equals the removable discontinuity. All right, so that can extend to pretty much any type of function here if there's a removable discontinuity. To remove a discontinuity, all you have to do is say g of x is equal to, and make a piecewise function. It's equal to f of x where x is equal to, let's just say it was had a removable discontinuity at c. And then the function is equal to the limit as x approaches c of f of x, where x is not equal to c up here, and where x equals c. So it's equal to the original function where x is not equal to c, and then is equal to the limit as x approaches that removable discontinuity of f of x, where x equals c. That's basically just colors in the dot right there. In this one particular function, another option, you could have just said g of x is equal to this function right here. This is called extending the function to remove the removable discontinuity. All right? And that gets us through exploration 1. And again, this trick right here is this trick right up Chihira is probably one of the most important ones that you can learn to remove a discontinuity, a removable discontinuity. You cannot do this with infinite discontinuities or oscillating or jump discontinuities. But as long as you have a removable discontinuity, just extend the function into a piecewise function, say equals the original function, where x is not equal to the discontinuity location, and the limit as x approaches that location of f of x, where x is equal to the discontinuity. So let's turn off sphere. Let's go down here and just say what we mean by a continuous function. A function is continuous on an interval if and only if it is continuous at every point on that interval. A continuous function is continuous at every point on its domain. See, I had an exclamation point, so I really had to get excited there. We're going to look at Theorem 6 and 7 on page 82 to allow us to check for more complex functions of continuity. All right? So Theorem 6, let's put my doc cam back up here. There we go. I'm going to hold it flat so you guys can actually read it. If the functions f and g are continuous at x equals c, then the following combinations are continuous at x equals c. Sums, you can add the functions together, still continuous at that point. You can take the difference, f minus g is still continuous. F times g is still continuous. Any constant multiple times f is continuous. And quotients, f divided by g is continuous as long as g of c is not equal to 0. And compositions of functions, a composition of functions is continuous as long as f is continuous at c and g is continuous at c. All right? Those are the two theorems. And I know that kind of stinks because you're like, but we don't know what functions are continuous. Well, actually we do. We know certain functions are continuous. Like if I was to draw a polynomial on a graph, I could draw a polynomial without lifting up my hand. And I don't care what degree it is. I know all polynomials are continuous. I know rational functions. As long as the denominator is not equal to 0, it's continuous. I happen to know that the cosine function just goes like that all over the place. Sine, same thing. Is the tangent function continuous? No, because tangent has those vertical asymptotes on them. The absolute value function, that's continuous. So let's look at some examples up here where we can complicate it a little bit more. So I look at y equals sine of the quantity of x to the third minus 4x plus 2 over absolute value of x plus 1. I happen to look at this and I know that this function is continuous, period, for all points, for all real numbers, really, because I look here, sine. Again, I know sine just goes like this. I never have to pick up my pencil for sine. Looking inside here, I have a rational function. The numerator is continuous because it is a polynomial. And again, all polynomials are continuous. I can draw them without picking up my pen. Down here, I happen to know that I've got an absolute value of x. Absolute value of x is continuous. It just looks like a v. 1, that's continuous. So the absolute value of x plus 1 is going to be continuous because it's a sum of two continuous functions. The only thing that can cause this function to be discontinuous at a point is if I can get a denominator to be 0. I look at this and right away see that the denominator can't be 0 because I've got absolute value of x. That's positive. positive plus 1, that's going to be more positive. This can never get to 0. So therefore, I've got composition of functions where the outside is continuous at all points. Numerator continuous, denominator continuous, and can never equal 0. Boom, it's a continuous function. Looking over here, again, I happen to know that cosine of x is continuous. I happen to know that absolute value looks like this, continuous, period. I don't have to pick up my pencil to draw it. So therefore, the composition of those two functions is continuous. Third one, we have another composition of functions, absolute value and a polynomial. Absolute value is continuous, polynomial is continuous, therefore, the composition of the two is continuous. I'm realizing now you might not have been able to see those functions, but these are the functions that I was talking about. Realizing that some of them are a little bit out of focus. But you can see right here, where I was talking about cosine of absolute value of x, absolute value of 2x squared minus 3x plus 2. And evaluating a function for continuity shouldn't normally take like 20 minutes or so. You can just look at it and boom. As long as all the pieces are continuous, the actual function is continuous. All right. Let's look at this. Intermediate value theorem. Whew, this one's fun. If a function is continuous between a and b, then it takes on every value between f of a and f of b. And this is one of those theorems that I classify them in a giant category of, well, duh. If you have a function that you can't pick up your pen to draw it, you have to keep your pen on the ground. What this is basically saying is, if you start over here and end over here, you have to pass by every height in between those 2 points. You might go outside of the boundaries. You're not guaranteed to go outside of the boundaries, but you are guaranteed to hit every height between f of a and f of b. And there's a picture to show it for you. And what makes things cooler? What makes things cooler? Something that makes things cooler is a joke. So I have a joke for you all. Why did the chicken cross the road? Legitimate question. Intermediate value theorem. What makes a joke funny? Explaining it, right? So intermediate value theorem. We said the chicken started at point A. He was on one side of the road. At point B, he was at the function value of f of b. F of b happens to be on the other side of the road. Why did the chicken cross the road? Because he started down here and he ended over here. Intermediate value theorem says since he started here and ended here, he has to take on every value in between those 2 heights. And what's in between those 2 heights? The road. So why did he have to cross the road? Because of the intermediate value theorem. His path is continuous as long as it's a continuous function. He had to have crossed the road. Now, of course, if we believe in sci-fi and any of that crap, we could actually say that this would be invalid if the chicken could teleport. But chickens can't teleport, and therefore his path has to be continuous. His location has to be continuous there. Aren't jokes funny when you explain them? The answer is yes. Is there something we could use this for? Yeah, sure. Is there any number that is exactly 3 less than its square? And the answer is, I don't know. So write down this question. So I'm going to switch over to my document cam because I don't think I have enough room down here to write. I'm going to write the answer on my document cam. And I'm tearing through this legal pad. Sphere. All right. Number 3 less. There we go. That's easier to write when I'm not on top of a book. Then it's square. I will ruin this for you, and I will tell you that the answer is yes. But to get to the yes, we have to look at how do we define this number? And that number is going to be x. x is equal to any number. And the question is there a number where x is equal to 3 less than its square? So less than minus its square, x squared. So is there a number where x is equal to x squared minus 3? And to answer this, I make this a little bit friendlier, and I get 0 on one side by subtracting x. I get 0 is equal to, let's see, x squared minus x minus 3. Now here's the tricky part. I'm going to say now a made-up function is equal to f of x. Or sorry, made-up function f of x is equal to x squared minus x minus 3. I'm just trying to figure out, is there a point where f of x is equal to 0? I don't have to figure out exactly what that number is. I'm going to show you how to, but in order to see if there is a number, all I have to do is find a value of f of x that is less than 0 and find a value of x where f of x is greater than 0. Because if I find those two things, since this is a continuous function, then f of x would have to take on every value in between those two values. Now I'm just going to make up some numbers. Let's plug in f of 0. F of 0 is going to equal 0 squared minus 0 minus 3. 0 minus 0 minus 3 is equal to negative 3. Then let's plug in another number. We can make a wild random guess. 1 wouldn't work because 1 squared minus 1, 0 minus 3 would be negative 3 again. If I tried 2, I would have 4 minus 2, so 2 minus 3 would give me negative 1. I'm going to try f of 3 because really what I want to do, I want to find out a value that gives me f to be negative and a value to be f being positive. So that somewhere in between those two would be 0. So f of 3, 3 squared minus 3 minus 3, 9 minus 3, 6 minus 3 gives me 3. Since f of x is continuous, f of x equals 0 for some x by the intermediate value theorem. And in my class, you're going to be all right abbreviating that as IVT. If you're taking the AP test with this type of question, you would be required to invoke the intermediate value theorem. So you would have to acknowledge somewhere that you're using the intermediate value theorem. And I don't think you would be able to abbreviate it. So honestly, I'm not sure if you could. It's probably better just to play it safe and not abbreviate it. All right. Here are some problems that you can try out before we have class tomorrow, but we will be working on these problems in class tomorrow. All right, this was fun. As per usual, please come again and see you tomorrow.